Welcome. Continuing the study of the improper integrals. In this video, I'm going to give introduction to the beta function or beta function. We have seen in the previous video what was a gamma function, which was represented by this symbol here, which means gamma of n, which was defined by this expression from 0 to infinity of e raised to minus x into x raised to n minus 1 dx. So this was the gamma function. Now the beta function, as well as the gamma function, though, are all part of the improper integrals. Now today I'm going to introduce what is the beta function and what is the relationship between the beta function and the gamma function. Now a beta function, which can be represented as beta, it has two arguments. In the gamma function it was only an n. The beta function is going to have two arguments. One of them is going to be m and the next one is going to be n. So its beta of mn is defined by an integration from 0 to 1. So this is the first difference we have. Instead of 0 to infinity, it's from 0 to 1 of x raised to m minus 1 into 1 minus x raised to n minus 1 dx. As you can see here, we have two arguments, m and n, while here only was n for the gamma function. Now one thing that happens here is that in the gamma function our n was positive. Here our m and our n all should be positive. So this is the concept of the beta function. Now when we're dealing with the beta function, we also have to use most of the times the properties that accompany these kind of functions to solve problems, and we have especially three properties. The first property we're going to see from the beta function is that if you have beta of n, it is equal to integration from 0 to infinity of x raised to m minus 1 divided by 1 plus x raised to m plus n. So this is our first property, which can be used when you're going to solve problems involving the beta function. So this we can call it as property number 1. Property number 2. Property number 2 says that it says that beta of mn is equal to beta of nm. So as you can see here, we just reverse this. Now what this property implies is that whatever is going to be the order of these two arguments, m and n, we are still going to get the same result. But how can we prove that? Okay, let us start by proving this by presenting the general formula of the beta function. This is the proof. We know that beta of mn is equal to integration from 0 to 1 of, this is going to be here, x raised to m minus 1 into 1 minus x raised to n minus 1 dx. Now we're trying to prove that this and this are the same thing. Okay, so the first thing we can do is that we can solve this thing by two methods. So let us assume that 1 minus x is equal to some other variable. Let's call that variable t, right? So this means that if you have minus, dx is going to be equal to dt, which tells us that dx is equal to minus dt. We have just changing out the function from x, a function of x, we're trying to change it to the function of another variable, which is a variable t, trying to prove this. Right, so now let us see what is going to happen with our limits. When we have limits here from 0 to 1, it means, because this is a function of x, it means this is our x initial, which is from 0, and our x final, which is equal to 1. So now we want to see what are going to be our next limits, which are going to call us new limits. What are going to be our new limits of our function expressed in terms of t, which is a function of t. So if x is equal to 0, here we're going to see is 1 minus 0. So it means that when x is equal to 0, our t is going to be equal to 1. X is 0 here, so t is going to be 1. Now the upper limit, if x is equal to 1, it means that our t is going to be 1 minus 1 is going to be 0, so our t is going to be 0. So with this, we have found out what are the next limits that we should use to express this function in terms of a variable t. Now rewriting beta of m n. You should know that this is the sequence that you're going to see these arguments here. M is going to come first, and then n is going to come here. Okay, so this is going to be equal to. Now we have just changed our limits, so our limits now are going to be, when x was 0 now becomes 1. It's going to be from 1 to 0, so it's reversed. We reversed our limits, and then the next point was this: x raised to m minus 1. We have 1 minus x is equal to t, but how is x? So it can just be like this. If you have 1 minus x is equal to t, this means that x is equal to what? X is equal, comes here, is going to be 1 minus t. Okay, so what I'm going to do here is just going to write 1 minus t, replacing that x raised to m minus 1, and then here I'm trying to replace this part here. We have 1 minus x already, so this is going to be replaced by t. It's going to have t raised to n minus 1, and then this is going to be, this is dx, but you know that dx is going to be minus dt, so you're going to give it minus dt like this. Okay, so then what we're going to do now, continue, we're going to have, this is a minus sign, so we can just put it out. We can just put it here. We're going to have here from 1 to 0 of this t here. Let us put it in front, n minus 1, and then you're going to have 1 minus t raised to m minus 1 dt. As you can see here, basically what we get here is a form which is close to the form that we use for the definition of the beta function. But these two functions, this one and this one, they're not the same. Why? 1, because of this minus sign, and 2, because of these limits. These limits are not the same limits as these limits here. So what you can do here is that if you want to eliminate this minus 1 here, what we do is just, this is what we're going to have. To eliminate this one, you just have to reverse the limits. So instead of 1 to 0, if you put 0 to 1, which means you're flipping the limits, this minus sign disappears. This is one of the properties. The minus signs will disappear. So we're going to have now t raised to n minus 1, and then we're going to have 1 minus t raised to m minus 1 dt. So to make this disappear, we had to flip the limits, and then that's what we got here. Now, if you have to write this function in the form of the beta function, which is this form here, it's going to be beta of, what is the first argument we see when we're writing this, when we read this formula here, is n. So it's going to become n first, and then the next one which comes here in the second part is m. So it's going to be m. So therefore, as you can see, beta of mn is the same thing as beta of nm. The other way in which this thing can be solved is by applying the theorem that says that, for example, we have a function with the limits 0 to a. This is a theorem which can also be used to prove this. We have, for example, from 0 to a of a function f of x. This can also be written as integration from 0 to a of, I'm going to have here f, I'm going to have here this is going to be f of a minus x dx. This is also one of the forms which you can use to solve this. You're going to get the same result. What you're going to do is basically, in place of all the x values that would have an original expression of the beta function, we're going to replace those values by the upper limit minus the value of x that comes. So it's going to be an easy substitution. So let us see, for example, how it would be. This is method 2, second method. So we know that beta of mn is equal to integration from 0 to 1 of, here it's x raised to m minus 1, and here 1 minus x raised to n minus 1 dx. Okay, so what we're going to do here applying this is that we're going to have, this is going to be equal to integration from 0 to 1 of, here we have x, but you're replacing all the places in which you have an x by the value of the upper limit minus that value we get there. So So this is going to be what? It's going to be 1 minus x raised to m minus 1, and this is going to be what? It's going to be 1 minus whatever we get here. It's going to be 1 minus x, all of this raised to n minus 1 dx. Okay, so if you continue solving this, you see that we don't do anything with the limits. So this is the shortest form of solving this. We don't do anything with the limits. We're going to have here 0 to 1, and then we have this, and then we also have the second part. You're going to have 1 minus 1, see, and then minus 1 is going to be 0. This minus and this become plus, so you're going to become x here. So this is going to become x raised to n minus 1 into this. Now is going to become 1 minus x raised to m minus 1. All of this is dx. So this is the second way of proving this is equal to beta of nm. So this is the second way to prove that beta of mn is equal to beta of nm. So this was the second property. Now the last property, the third property, is that a function, beta function of mn is equal to, now we want to, it's this actually, it's the equivalence. How can we write this expression again now using a trigonometric form? So this is going to be integration from 0 to pi by 2 of sine of theta raised to 2m minus 1 into cos of theta raised to 2n. Actually this is all this raised to 2n minus 1, all this thing into the theta. So this is the last property we are going to use when we're going to solve problems. This is the equivalence of the beta function of m and n. Now in order to prove this thing, it's easy. We basically have to take first this x, makes x, we have to make this assumption that x was equal to sine square of theta, and then we differentiate this, and then we make substitution, and then we come to this solution as well. The next thing that you're going to see in this video is the relationship between the gamma and the beta function. So this is going to be called relationship between gamma and beta function. It can be summarized as this: beta of mn is equal to gamma of m into gamma of n divided by gamma of n plus n. This is the first and very important relationship that you're going to be using in most of the problems that you're going to be solving in next videos. Even most of the problems may be finding in your exams and your manuals, they're going to use most of the times these kind of properties to give us the value. There is also another formula which is called Euler reflection formula, which is also one of the very important relationships that you should always remember. Gamma of n into gamma of 1 minus that same n is going to be equal to pi divided by sine of n pi. So these properties are very, very important, and going to be applying them from when we start solving problems. So thank you.